Hello, everyone. Thank you so much for coming. If you could please turn on your cameras, that would be great. Today we have Miss Knobloch and Miss Burrell speaking with us. Miss Burrell will be talking about the Chicago Engineers Foundation scholarships for engineering students, which encourages Chicago students to pursue engineering by recognizing their talent through merit-based financial awards and career development opportunities to help achieve their engineering goals.
Good morning, everybody. I'm Debbie Burrell. I'm the Executive Director of Chicago Engineers Foundation. And before we hear from Madison, and she is, of course, our most special guest today to talk about renewable energy engineering, I just wanted to take a few minutes to say hello and tell you about some scholarship opportunities that are just right for those of you who are graduating seniors or maybe getting ready for your senior year, and specifically for those who are planning to study engineering in college. So that was weird. Sorry about that. So the Chicago Engineers Foundation has a merit-based scholarship award, and I just put our information into the chat. I'm going to share a quick screen with everybody to tell you about our merit-based awards. They are renewable. So if one gets an award this year as a graduating high school senior, you can continue to apply through 4 years of undergraduate study. And as long as you continue to meet eligibility requirements, you are eligible for up to $5,600 over 4 years. And in addition to that, we also offer mentoring and career resources to all of our award recipients. So help with resumes, we help with interview skills, we do mock interview sessions, we have workshops. And everything right now is virtual. We hope to be able to bring back some in-person stuff soon. But for right now, it's been great for our students who tend to go to school literally all over the country. You can keep in touch with us and have access to a mentor, any sort of career resources that you might need while you're on campus, wherever you might be. So for our class of 2022, which is of course our graduating high school seniors, as long as you live or go to high school in the city of Chicago, you can apply for our award as long as you are planning to study engineering, any type of engineering in college, starting with fall 2022. We have an application that is online that you can either access through our website, which is chicagoengineersfoundation.org, or if you are a CPS student through Academic Works. You basically go through that application. It takes about an hour or so. You'll upload an acceptance to a school, whether or not it's a school you absolutely plan to go to starting, in the fall. That's okay. We know that a lot of acceptances are still coming in. We just like to see something, of course. You'll show us your transcripts. You'll do some short answer essays, complete it all by April 1st. And then we pick our class of 2022 right around May or so. And around June is when we literally hand our award recipients a check. And for our graduating high school seniors, it's $1,200 to start. This is a great opportunity to not only, of course, apply for scholarships, but as I said, to have access to career resources and mentorship with engineering professionals from all over the city of Chicago. We've been a scholarship provider for about 50 years. Over that time, we've given away well over several $1 million in scholarship opportunities, and hopefully been very helpful to our alums in helping them work on their professional presence and build their professional resources while they are still in college and onto that career path as an engineering professional. If anyone has any questions about, just a minute, about our scholarship, I'll hang out for just a minute. Otherwise, you're more than welcome to, again, take a look at the resources in the chat, chicagoengineersfoundation.org. We also maintain another page called Scholarship Resources on our website, which I linked there as well. Not just us, but every other engineering scholarship we could find for students here in the Chicago area. So you're welcome to take a look at that, or email us anytime at CEF@chicagoengineersfoundation.org. Does anyone have any questions before I turn it over to our special guest, Madison? Awesome. Well, I'm seeing a lot of great future engineers here. Hopefully we'll see a lot of you in our scholarship portal. It is open now and open through April 1st. Again, any questions come up, please feel free to reach out anytime via either our social pages our website, our email. We would love to see as many case members as possible applying for our scholarship opportunity and all the other ones that are available to future engineers here in Chicago. Thanks so much, guys.
Thank you.
So now we'll go to Miss Knobloch here. She is a design engineer with EDF Renewables North America. She graduated from the University of Wisconsin-Madison in 2019 and has around 5 years of experience in the field. And here she is. I'll let her have the floor.
Thanks. All right. Again, I'm Madison Knobloch, and I am a design engineer, and I design solar farms. So I'm here to talk about primarily renewable energy. And I think this should be the right screen. Can you guys see my screen?
Yeah, we can see it.
Cool. All right. So, like you said, I graduated undergrad in 2019. So I did college really recently. So I have a couple of college engineering tips for you guys at the end of my renewable energy part as well. So, all right, let's get going. I decided that what I would have wanted to know in high school where you guys are at is all of the like possible jobs and majors that I could have like had. I just never knew about. When I got into renewable energy, I kind of just fell into it. I applied for a random internship and ended up getting it, and it was the coolest thing. So in possible fields, we got solar, and within solar, there's lots of different things you can do. There's photovoltaic, concentrated solar, and thermal. I'm going to go into all of these in depth. This is kind of just my summary slide. We got wind, onshore and offshore, geothermal, lots of different types of geothermal plants. Got biogas, anaerobic digestion, and algae. Biomass, lots of different things you can make into energy if you burn it. Hydropower, lots of different hydropower going on. Hydrogen fuel, I think you guys have probably heard of hydrogen powered cars that are being researched. Lots of different types of nuclear plants, and we'll go into the question of nuclear energy, is that renewable, a little bit too. Batteries, just as important as all of the rest of these. And a couple of other fields within renewable energy. There's energy sustainability, which a lot of times you go and analyze HVAC systems, some like air conditioning and heating systems within buildings, and try to make them more efficient. And decarbonization, also very important in, it's not necessarily a renewable energy, but taking carbon from the atmosphere is just as important as not putting more into it. So solar, this is this is the kind of thing that I would design in my job. And I'm a solar engineer, so I'm going to be a little biased to solar, but this is the type of solar panel that tilts with the sun. And I can tell that because it's only got one row of panels. So then we got, this is just a quick how the solar panel works. And I put these throughout the slides because like every time I have a diagram, there is an engineer who designed it. There's an engineer who produced it. There's an engineer behind like every step of all of these like renewable energy diagrams and images. So I find that really cool that there's someone for everything. So we got our positive, our P type semiconductor, and our N type, which is our negative semiconductor, and the photons excite the electrons. And there's this depletion region where it has trouble to pass the electrons to fit the empty positive semiconductor, the electron holes. And when we attach a conductor, we create a current, and that is how we get electricity from solar. So this is a concentrated solar farm. These are really cool. You'll find them in like Arizona, New Mexico. This is a bunch of mirrors or reflectors that reflect the sun to this, area up at the top of the tower. And that is heated and heats a steam turbine and creates energy by the steam turbine. So this is kind of how that works. We got a lot of different types of concentrated solar. These are all under the concentrated solar field. Some of them use solar by heating a either water or a conductor within the reflector. That's what the parabolic trough is. We got the reflectors and the central receiver, which we just saw. And there's some huge parabolic dishes too that also reflect into a center. We got solar heating. So these are tubes of water and they just run on the top of your roof and then they connect to your boiler, which is kind of cool. It means your boiler doesn't really have to do any work. It's the sun that's warming your water. So just like you can have solar panels on your house, you can also have solar heating panels on your house. Wind, we got onshore, which is probably what you guys see if you, drive really anywhere in the Midwest. And we got our driveways. So cool things about, we got a question. How efficient is solar if there's a lot of weather changes? That's a really good question. So it's funny you ask. My projects right now that I'm working on are in Maine. And Maine is like the northernmost that you can get. So it's not like sunny all the time like some of these Arizona and California solar farms. What's interesting is solar panels actually perform better in the cold, but cold weather is typically cloudier or more precipitous, and you're going to have less sun actually available. So it's definitely a give and take, but it does kind of let us justify building solar almost anywhere, because even if it has bad weather, the solar panels are going to be more efficient because they're not overheating, they're staying cool in the cooler weather. So hopefully that answers that. I will also get to, there's a key question for that also kind of relates to that, in why it's called, I think, intermittent energy, where just like, so wind and solar, they obviously can only give energy to the grid if there's wind or there's sun. So not all the time, which is the point. Whereas our coal plants or our natural gas plants, we are feeding them constantly. So we can get energy from those at all times of the day, rather than just when the sun is out or just when the wind is blowing. So I guess that also does, like, the weather will affect when we can get energy as well. So here's our inside of a wind turbine. We got the wind that is blowing the turbines, which is turning the shaft and the gearbox. And inside of here, we got just kind of like our solar panels. We were creating AC with the turbine, right? Because AC can go back and forth, whereas DC is direct, right? DC goes just one way and AC is alternating. So the wind can blow either way, which is why we have alternating current. But the issue with making AC from a wind turbine is that it's something called wild power. It's literally not tame power. So we have to convert it to direct current and then convert it back to a specific AC current in order to tame the wild AC that comes from a turbine. So that's what some of this equipment inside is doing. And like I said, there's an engineer that does every part of this. There's an engineer that, like a civil engineer would see if the land is okay to put a turbine in. There's product engineers or component engineers that would make each specific part that goes into a turbine. And there's an engineer kind of like me who looks at the entire field and researches the resource. So what kind of wind speeds and what direction of wind speeds do we normally get in this region, and how far away or how close can I put these turbines, and how much can I fit on this field to get the maximum amount of energy off of the field that we're paying for. So then we got offshore, which I think is really cool. The USA only has one built offshore farm at the moment. That's in Block Island, Rhode Island. And Europe is like way farther along in like most renewable energies than the rest of us. So obviously this is a picture of a European offshore farm. And because the Block Island one has 5 turbines, it's kind of sad, but a lot of renewable energy companies right now are just getting into offshore wind. It's really like interesting and challenging engineering too, because we got to look at where the surface is below the water and how much we want to, how many megawatts, how much power we want to get from this plant. So these are some of the different foundations. We'll need really good civil engineers to be able to figure out how to put these foundations and connect them to the ground so our offshore plants don't blow away, because that's good. Don't want them to blow away. All right, got geothermal. Here's a geothermal plant, and we have a couple different types of these, and these are going to show up where there is a natural geothermal resource. Like Iceland is huge on geothermal. So we got a dry steam power plant, and this takes steam that's coming out of the ground. So it's already steam when it's in the ground. It turns the turbine, and then we inject it back into the ground. So kind of a renewable cycle right there. We got flash steam, which brings hot water from the ground. We turn it into steam, turns the turbine, inject the water back into the ground. And then we got a binary cycle, which takes any liquid from the ground, whatever form it's in, and that liquid heats another liquid by just proxy, by being right next to it. And that liquid, usually water, turns into steam, turns the turbine, and then we inject what was initially in the ground back into the ground. So obviously there's a lot of questions, just like there is with fracking, about the stability of ejecting things back into the ground, especially if they're at a different state of matter than how we got it. So that takes a fair amount of civil engineering. There's also, depending on how big of a school you go to, there is geological engineering that would have a lot to do with this, especially like further below, like in the layers further below just the top layer of the ground. So we got biogas. Oh, by the way, I'm a trained environmental engineer, but I probably do more electrical engineering in my job at the moment. So I learned primarily a lot about biogas, biomass, things that we can get from the environment. That's what I learned in my major, but very applicable when you get to the electrical side. So this is an anaerobic digester. And you might have seen these if you're driving in Indiana or Wisconsin. You can put different digested materials, different animal related materials into this digester, and anaerobic is obviously no oxygen. So we got to pump the oxygen out, and it breaks down and creates different gases, not all methane, not all carbon dioxide, but different gases as it's decomposing. And we process the gases and can use it as this is renewable natural gas. And can go also into the grid. This, I believe, is our algae farm. And this is definitely a newer renewable energy where they grow tons of algae and then process it. It's very, very complicated, but this is the kind of thing that people who would be like a research engineer kind of job, and you'd probably go into chemical engineering if this is something that you wanted to do, and work through all of the chemical processes in order to create usually diesel for trucks that come from algae. So this is a huge potential field, but still growing, and we're still learning about it. Then we got biomass. This is a biomass plant, and I believe those piles back there are either wood chips or wood pellets. And these are all of the different types of things that we can burn to create energy from these biomass sources. I think landfill gas systems are pretty cool because landfills kind of just sit there and die, and we feel bad about all of the waste that we made, but hopefully we can make electricity from them if we build the landfill right. So we got methane and CO2 that comes from the landfill, and we process it a little bit, take out the moisture because we don't want to burn that. There's a flare that cleans some of the gases, so it's ready to be able to use for fuel or electricity generation. This is also a note that I wanted to make, because as you see, we headed too fast. I was saying that we burn all of these sources to get energy. And one astute observer may ask, how is that renewable if we're burning things just like we're burning coal? Well, that is a very good question. There is something called life cycle analysis or life cycle assessment that engineers in the renewable energy field often either complete or often work very close with. And that is basically asking the question of what is the environmental impact from the beginning of, from raw materials. We take it from wherever it was, and we manufacture, package, distribute, use, and dispose. What is the environmental impact of every single part of the process So biomass is, it's like a really questionable, like we're still putting CO2 into into the atmosphere when we're burning things, but they call it renewable because we can grow back trees. The cows will still be producing manure. We can grow corn and still, burn it. So theoretically, because we can grow it back, unlike coal, where there's a finite amount of coal theoretically in the earth, we would run out of that eventually. We'll run out of oil eventually. But if we keep growing the biomass, we will still have energy. So it's definitely good. It's a good use of some of these things that might go to waste to begin with. It's also another decent alternative for farmers who are not finding profit in their normal farming ventures. But it's definitely not the cleanest renewable energy, which is kind of paradoxical, but it's definitely something that engineers are needed for, and their engineers are trying to make more efficient and trying to make more renewable and trying to make cleaner. And that's one of the things that you guys could do eventually. Hydropower also I find really cool. I'm sure you guys have heard of the Hoover Dam. This is not that, but it's a dam. And if you guys have taken physics, there's you got the potential energy of having the water at the higher location, and you pump it down at a slower rate than, or I guess a pressurized rate than it would normally go, and it runs through the turbine and creates electricity with the potential energy turning to kinetic. This is tidal energy, also very cool. These are wind turbines at the bottom of the ocean, and they are turned by the back and forth movement of the tide. And these are still definitely in the research stage. They're definitely still being questioned on whether it can be promoted on a larger scale, because they have issues with animals or fish disrupting their migratory movement if they run into them. And it's interesting too, less so than birds hit wind turbines. Birds, there's been a lot of studies because people are like, oh no, the birds, the wind turbines are killing them. They're not that much. There's usually sound that we've engineered to emit from the turbines to dissuade the birds from coming close to the wind turbines, but we're still working on that with tidal power, especially because there's electromagnetic field that is created by the electricity that they're creating, and that can also, the electromagnetic field and the noise from the turbines can interrupt echolocating animals, which is kind of a bummer, but people are still optimistic and they're still doing a lot of research on tidal power. These don't necessarily look like renewable energy, but this is a small piece of a wave power plant. So the tides go in and out, and they're at the bottom of the ocean, and the waves are at the top of the ocean. And this is also still way in the research phase, trying to figure out how best to capture the waves, especially if something like this can move with the waves too. So how do we get the waves to move through it? How do you get different sized waves to be captured? In my time as a solar engineer, I got to work with someone who did their PhD in wave energy. So there's a lot of research to be done, and it's also good to know that things that he learned in his PhD in wave energy were super transferable to working in a productive solar industry. So I don't know how much money you're going to make in producing multiple wave energy farms across the world, since they're not scalable yet. But he was able to transition right into photovoltaic solar, which is scalable. So that is cool to know. And it's also cool if you want to be a research engineer to look into these and try to make them more efficient and make them less impactful on the environment that they're in. Hydrogen fuel. So this is their hydrogen fuel plants, not necessarily in the US. I think this one's in Korea. But they can be scaled, and you might have heard that they're making hydrogen fuel cars, which would be super cool, especially because you kind of just put water in and it separates the water. Kind of like if you guys have learned about galvanic cells or galvanic batteries in your chemistry class, this is a little bit like that, and you just create a potential using using your hydrogen and your water, and the current can flow to kind of satisfy that potential. So that is also really in the research energy. We're trying to make it more efficient, trying to make it cheaper, because hydrogen cars would have been scaled, you know, if they had been cheaper. So still working on that. Nuclear. So this is, as you would normally see, a nuclear plant on the water. And these are the two most common that I'm showing you guys. This is a pressure water reactor. So we got our reactor with likely our uranium oxide and a pressurizer, and the uranium oxide is slowly going through fission, and the fission reaction heats the steam, and the steam will turn the turbine. So you probably started to see a pattern, as most engineers would, like a lot of these have steam turbines, and a lot of them just have turbines in general. So that is something that I have taken from my college classes, because we do a lot of engines in engineering, as you might guess, because it's in the name. And then we got our condenser, and this is the water that is coming in from the lake or the pond or whatever body of water that it's on. It's cooling the reaction, the fission reaction, because we want it to go slow. That's really important part of nuclear, and we put it back into the body of water that it came. So that's also another usually qualm that people have with nuclear, is that there's sometimes heat pollution. Yeah, we're going into the downsides of nuclear, that's for sure. Heat pollution, which means we're taking water that it's likely cool from the lake, and we are putting it back hotter than it is, and that really affects migratory fish and other migratory species, because they move depending on the water's temperature. So that's really not great. Other potential downsides to to nuclear are nuclear waste. How do you get rid of the uranium when we've completed the fission reaction? Other downsides to nuclear are, people think that if they have nuclear reactors going, nuclear science going, that they can potentially also have nuclear weapons. That's not a great thing. People are really afraid of nuclear accidents. Everybody points to Chernobyl or 3 Mile Island. And also the scalable ability for nuclear is also a downside, because it has to be near a body of water, which reduces the amount of places we can put it significantly. There are some, counterpoints to some of those downsides. For the nuclear waste downside, people have figured out, engineers have done their research, and they're like, there's this huge salt crypt, which I hadn't heard of until I started learning about nuclear in Arizona or New Mexico. And they can put thousands of years, they can bury it in this salt crypt, and it should not really affect anything other than, it shouldn't seep into the ground, which people are worried about. It shouldn't cause radiation to the neighboring villages. So the concept has been solved, but the practicality of it and shipping the nuclear waste to there is a potential issue. And a lot of the nuclear accidents, I guess people are worried about radiation that comes with living close to a nuclear plant. And there have also been studies on that saying that the radiation that comes from a nuclear plant is ever so slightly larger than what a normal American would be, I guess, privy to in their life. So because you get radiation when you're you're getting an x-ray, if you break a bone, or if you go in a plane, there's a slight amount of radiation. Your phone, obviously a slight amount of radiation. So there has been research to try to counter that. The other really big thing that people are pushing for nuclear plants is the concept of peak plant potential. So this, like our wind and our solar, or unlike our wind and our solar, we could have nuclear plants running at all times of the day, 24 hours. Whereas wind obviously can only come when the wind is blowing, and solar can only come when the sun is shining. So that a lot of people are saying we could completely replace coal plants into nuclear plants, because we could run nuclear plants at all the time. And when our energy use exceeds what a wind farm or a solar farm could provide the grid, we can use this peak plant at the peak of our electricity usage and that could be a nuclear plant. Okay, so we got a couple of other questions. In general, do steam turbines produce DC and need to be converted to AC for the grid, or do they just produce AC? They produce AC, and usually they need to be converted to DC and then converted back to AC for the grid. Sometimes I think it's on a really small scale. You can let the turbine generate AC and let that like slightly wild AC go straight into the grid. But on larger scales, on scales where we're designing larger wind farms, we're going to want to make sure we can control that AC power and convert to DC and convert back to AC. Hopefully that answers that question. Does nuclear power, fission specifically, deserve the reputation that it has? That is a really good question. From a science perspective, I don't think so. From a science perspective, a lot of the nervousness has been disproven, and obviously no one wants anyone to be hurt by any kind of nuclear reactor disaster. Those happened a fair amount of time ago, Chernobyl and 3 Mile Island, and I think there are a lot of processes in place that we help to avoid. And especially as I am an engineer, we have probably 3 or 4 core values that we do all of our engineering by, and one of the biggest ones is safety. We have safety checks before we go on site. We have safety checks when we get off site. We have to make sure we're wearing all of the correct PPE, which you guys might have learned about in COVID. There's different type of PPE when you have to go onto a construction site, onto a nuclear power site. So people take a lot of care for safety in all engineering industries. It's one of the most important things that you can learn about and that you don't discount. But it's obviously still something that people worry about, and sometimes the public completely influences the field or whether it's a viable energy resource. So for another example of how the public is influencing energy sources, we have to, when we build a solar farm, we have to, get okay from the neighbors, because a lot of these are on old corn farms or something. And sometimes we have an old lady saying, my horses are not going to like the radiation that comes from a solar farm. And we're all like, what? There is a slight bit of radiation that comes from a solar farm, but it's negligible compared to living next to a airport or something. The old lady could potentially just shut down the entire solar farm if she does not want it next to her land. So that's one way that public could influence that. All right, I think we got a couple of other slides. So this is so we just had a pressure water reactor, and this is a boiling water reactor, a little less common, but still there are plants that do that. And it just has the water straight on the uranium creating steam. And then we got the condenser, which cools the reaction. So pretty similar, just not pressurized in this situation. And then there are a couple of other nuclear reactors that are out there that are less frequent, and there are very few plants, but they're definitely still in the research phase. There's also, depending on what school you guys go to, we had a nuclear engineering major, and there are not a lot of people who go into it because of, all of the questions around nuclear energy, but it's really fascinating and it's really needed, and it's also pretty hard and challenging. So I definitely recommend that to people who want a challenge in college. Other nuclear reactors that we have there's a fast neutron reactor, also called a sodium cooled reactor. We also have an advanced gas cooled reactor, and then there's light water or graphite moderated reactor. So that means that rather than being cooled by water, it's cooled by either light water or graphite, liquid graphite, or there's also heavy water that can cool. So that's like, I think it's deuterium, if that's the way you pronounce it. So like water with an extra H, maybe, something like that. Batteries. Batteries are not necessarily a renewable energy because, you have to, they eventually die. But they're super important, which is why I have them on the same page as the duck curve, which is also very important. I think I talked a little bit about already. Super important for the energy fields. So this is a solar plus storage. So the importance for solar to have storage, we have on this graph, we have our solar output here in gray, and we have the normal, the load that we normally get in blue. So normally at evening hours when we're cooking and eating dinner with our family and watching TV, that is when we're using the most energy, especially when it's not light out. We have to turn all of our lights on. And when you add solar into the grid and use solar instead of some of the other things, we create this orange line where we have decreased our use of the coal or whatever else is coming from the grid if we're relying solely on solar. And it kind of looks like a duck, which is why it's called a duck curve. Like there's the head over, there's a head over on the right and the tail on the left. But batteries are important because we can store some of the excess energy that we get from solar that we don't use during the day and use it during these other humps of the day when the sun is not shining. And batteries are also important for wind farms as well. They make this less of what I have called an intermittent energy. We're less reliant on the sun because we can have batteries. So sizing these batteries, designing these batteries, all things that there are engineers who do. And what else do I have? Oh, okay. So I've talked a little bit about this. Here are some of the potential jobs that you could go into and what kind of majors might be good if that's something that you want to do. So a research engineer would be working on energy that hasn't come onto the market yet. So that'd be like probably algae, that'd be wave and tidal energy. That would be, I didn't have it on my solar slide, but there's a lot of research going into thin film solar right now, where they're basically just like printing like the thinnest solar panels, and they're thinking of like we could like paint this onto roads, and our roads could literally be solar roads, which would be super cool. So research engineers do really important things. They have like really challenging and interesting jobs, and some good majors to go into if you want to focus on like the leading edge of science and renewable energy. Material science engineering, those people are the ones who figure out like what chemicals, what materials are the best kind of things to go into solar panels, are the best kind of things to create the turbines of the wind farms. They're creating the materials that we use for renewable energy. Chemical, biological, they're probably doing more of the algae. Chemical, you'll probably get alongside material science in solar as well. And electrical, you will see this in most of the bullets that I put up here, because it's important to understand the grid and how electricity works if you're going into an energy field. So quick on these other ones, sales engineer, these are the ones who are trying to sell what you're engineering. So you know every part of the engineer and what you're engineering, whether it's a product or whether it's like a whole solar farm. And I was a sales engineer for a little bit. I was designing like the bare minimum of a solar farm. And then we were showing that to potential owners of solar farms, saying, this is what you might get if you work with us. So that's really cool. You get to work on a high volume of sites or a high volume of products if you're a sales engineer. A design engineer, this is what I do. I design basically everything from we get a piece of land to the entire like electrical portion of when we're attached we've attached the solar farm to the grid. Project engineer, also sometimes a project manager, also sometimes a construction engineer. These people are working on how do we build the farm, how do we implement whatever energy we're doing on a schedule in the most efficient way, in the most price or cost efficient way as well. So project engineers are really, really important if you want to be like on site and working with the things you're actually engineering. You're like very hands-on. Project engineer is probably what you want to be. Whereas a sales engineer and design engineer, we're pretty much behind a computer most of the time. As a design engineer, I do get to go onto the sites that I design a couple times, but I'm not there every other day. Energy engineer is what I talked about a little bit there, working on efficiency of the energy that we already have, or also if you want to work for a utility, which they regulate our energy, and that's something that you would look into, and you'd want to focus on electrical engineering as probably your major. We got another question. Are current energy storage technologies sufficient? And if not, what do you think the future of energy storage is? I think a lot of them are sufficient at the moment, but sufficient technologically, not necessarily sufficient price-wise. I think these batteries are huge. I had a picture of them, and they're kind of pricey. And a lot of times we don't just have one battery, we have like 2 to 8 batteries on a solar farm to make it feasible in order to react to the grid in a way that we would require if we're only relying on solar. So I think it could go a little bit of a longer way for the tax incentives and the subsidies from the government to help with the battery process and getting that up to speed with the wind and solar industries, and helping that make it a little cheaper so that potential owners of solar farms would be interested in having a battery on their site. Because a lot of them are like, we only really want solar right now because we can get a lot of tax credits, and it won't be that expensive for us. but if you add the battery, it's going to be a lot more expensive. So that's the main issue with that at the moment. What I do, so this is my most recent site, and this is the like almost the front page of my design. So I have these kind of vertical lines. Those are my solar panels, all in a row. And I have to show where the fence would be in regards to the road and the property lines. And I have to do a lot of research into basically my main responsibility is knowing the electrical rules or the electrical code. And I have to know when I'm designing this solar farm off the top of my head that I cannot put a solar panel within 16 feet of a fence. Otherwise, the fence will have to be grounded, because technically, if it's a metal fence, it could be potentially energized if something breaks or something, like there's like an arc flash or something, like just like electricity on the loose, and we could have an energized fence, and that would be potentially catastrophic to someone who would come into contact with an energized fence. They could get severely electrocuted. So I have to know a lot of different places in the electrical code that allows us to create the safest solar farm. And I also have to be an expert in how to create the most efficient solar farm. So we have there, like right in the middle, there are what we call equipment pads, where we have things like a transformer, a combiner, an inverter, where we attach all of these solar panels to. And I have to know that as when we hook up the solar panels, when the equipment pads are the most centrally located, there is the least voltage drop along the run of DC coming from the solar panel and AC going to the grid. So that's a little jargony, but it's just an example of things that I have to know when I'm designing my solar farm. And this is another portion of the same design. I basically am laying out all of the equipment that we procure for the solar farm and telling the people who will be constructing it, this is how everything connects to itself. This is the size of everything. These are the amps, these are the volts, and this is how you connect everything in a safe and efficient way. So that's kind of what that looks like. I remember when I saw this for the first time, I'm like, dang, that's real electrical engineering. Okay, resources for high school and college students. These are things that you guys can look into now and like your freshman year of college for if you want to get further into renewable engineering. National Renewable Energy Labs, NREL, Department of Energy, SULI, Science of Undergrad Laboratory Internships, Women in Renewable Energy. There's a whole club, there's a whole nonprofit for women in renewable energy because there are very few of us. So there are scholarships that are just for women too. And in college, there are competition clubs like the ASHRAE or the Department of Energy College Wind Competition, where you create a club on your campus and you build a turbine and you compete against other colleges to make the most efficient turbine, which is kind of cool. So if I go onto the NREL website, that's what that looks like. You just start researching whether like the research participant program is like what research engineer might go into. There's lots of different labs that you can work in as an engineer. If you are going to community college, they want to get everybody involved in renewable engineering. So if that's where you're going, then there are options for you too. Some of my tips for when you go to college, I learned the most from my internships, and there's something called co-ops, which is kind of like studying abroad, but basically doing an internship instead of classes. So I did a co-op in Boston, and I was there for a semester. I got class credit and I got paid, which is kind of cool. So I wasn't in classes, I wasn't on campus that semester, I was working, and I learned so much. So I highly recommend doing as many internships as you can. Just start looking, you know, freshman year, summer, looking into who can take freshmen, because not all internships take freshmen. Because like I said, I did, or I don't know if I said this, I did this 2 years ago. I am 2 years out of my undergrad. So I did this really recently. Other biggest things, engineering is really hard. And I'm not saying that to scare you. I'm saying that to make sure you guys are very prepared. I was pretty good at math and science when I was in high school, and I got into engineering, and everybody is really good at math and science. So what I found out is that the people who get A's in college engineering are the ones who show up to something called office hours every time they hold it. So that's like the professor or the TA is holding an extra session outside, and they do it once a week to just let you ask questions, and they can help you. Like, they literally have started me on a problem and ended me on a problem, and like, I would not have been able to do that problem without their help. Thank goodness I went to office hours, because kids who don't go to office hours have a really hard time, because you don't always get to ask your questions in class. So ask for help, go to office hours, biggest thing I can recommend. Totally okay to take longer than 4 years. I took 4.5. Lots of engineers take 5 years, just because like normal class load is like maybe 15 credits. And if you take like 12 credits, like you're way more likely to get a better grade, because you have taken time to learn the things that are in your class. You can totally study abroad if you're an engineer. A lot of people think you can't, but you do want to talk to your advisor like right at the beginning of when you enter college, saying, I want to study abroad. Is that possible? Because you have to save specific classes for studying abroad, because I have a friend who studied abroad in Denmark, and there were only like 3 or 4 classes that she could have taken, because they only offer specific ones. So she saved all of those classes for when she was in Denmark. So definitely plan ahead, but you totally can. And take your FE before you graduate. That is a field engineer certification or license. And there's one for each engineering major, and that's the first step into becoming a professional engineer. If you see anybody with a PE at the end of their name, that's a professional engineer, and you have to take a test to get that license, but you also have to take your field engineer license, and it's the easiest when you do it like right before you graduate. So I assume that your advisors and your teachers will remind you of that when you're a senior in college, but I know a lot of engineers who get out into the working world and they haven't taken their FE, and they want to go and get their PE license, and they can't because they haven't taken their FE. So, and a lot of things you forget, because the FE is very widespread topics, where the PE is very centered on your topic. So I know I'm going a little over, but if you guys have any other questions, I'm happy to answer, as long as you guys have time. There's another one in the chat. What is the cleanest renewable energy? What's the environmental impact of manufacturing? And do the benefits outweigh the downsides? The cleanest renewable energy. Well, that one, like, you'd have to think about the life cycle assessment, the life cycle analysis that I went over, and especially for like even solar and wind. The United States market is not old enough to have to reach this question yet, but eventually the solar panels will not be efficient enough to justify the price we're paying for them. So eventually, in all of our contracts, when we build a solar farm, we say we promise to take this solar farm down and restore the land to what it was in 30 years, because that's about when the solar panels will have degraded enough to not be worth the price. So what do you do with a solar panel when it doesn't work for you anymore? And that's a really big question that people are just now in the United States starting to work on, but in Europe, they have pretty decent infrastructure in place where there's a lot of recycling that you can do with the steel, which is probably why I'd say, I think wind might be the cleanest because it has the most pieces of a turbine that you can eventually recycle and hopefully use that into something else. So thinking on a cradle to grave, like from the beginning to the end, I'd probably say wind is the cleanest. Environmental impact of manufacturing, and do the benefits outweigh the downsides? Yeah, I think it's actually interesting too. When I was on one of my very first solar farm visits, when I was like personally at the farm, and they were in the process of construction, they were cutting down trees to be able to build the solar farm in that place. And I'm like, what? This is like the antithesis of what we're trying to do. But then someone said there's a bunch of studies that say that the solar farm is doing more work than the trees were in that case, which is really sad. I'm like, please plant the trees somewhere else at least. But I think there is definitely a lot of manufacturing and building that aren't always taken into account. And as we get closer to our goals for 2050 and clean world in 2050, that we will have to address. Is it a problem that farmers can find producing these biofuels more profitable than growing food? I don't think so yet, especially because we at my solar company, we buy a lot of farms, like corn farms or soybean farms that aren't profitable anymore, to build a solar farm on too. So they're not just growing biofuels, they could also sell their land to a solar or a wind farm. But I think a lot of farmers are very set and attached in what they know, and they're not going to change unless they have to. But that is a generalization, and I don't think we have seen, usually when we approach farmers to try to build a solar farm or try to get them to start an anaerobic digester on their site, it's a long convincing process. We have to talk to them, we have to educate them a lot in what the pros for them would be and what their land would look like. So I don't think it is a problem yet. I don't know if it would be a bad problem, because they're creating energy that's somewhat cleaner than coal. So hopefully that answers that. Does the life cycle assessment factor in how something may reduce a different gas, like in the instance of fracking, which increases methane but supposedly reduces CO2? Oh, totally. That's why people think natural gas is, somewhat better than coal, because it's just a little bit cleaner. So I think that's one of the things that we weigh some of these renewable energies on is their life cycle assessment, and not, because we don't want to assess these renewable energies just on will they make us money, because a lot of people do that. That's why coal is still running, and that's why natural gas is still running. I think you've probably maybe seen, I think there are some public buses that are run on natural gas, and they're really proud of running on natural gas. They're like, we don't do diesel. So it's slightly cleaner and slightly better, I think, than the diesel that we would get. So never thought of the what to do when you don't need it anymore. I know, it's I like we have to find ways to hopefully recycle all of these components, and we need engineers to do that, especially in the US. And that's like, if that's something you're interested in, I would recommend probably going into material science engineering or mechanical engineering. You can go into mechanical engineering, you can do anything. So if you don't know what you want to do, I recommend mechanical engineering. And you have all of the doors open to you. But material science engineering, that's going to be like, how do we split this up and melt this down, and what can we reuse? So do I hear anything about Dyson spheres or swarms as a renewable energy source despite its large scale? I have not, but that's really cool. And I will see if any of my colleagues have, but I have not heard anything about Dyson spheres. That's really cool. What do you think the future for fossil fuels are? Will we be able to become more dependent on renewable energy? And is the Paris Agreement realistic? Ooh, okay. Well, as someone who's like got a little bit of environmental warrior in me, I think, and like just like this much socialism, you're like, you know, if the government paid for it, we could do it, right? Because I think like Scotland and Ireland and Iceland and like the Nordic countries, they're like really in on the offshore wind farms and the geothermal plants. They are actually like, and they're obviously smaller countries, right? Much smaller scale that they have to address, but they are, and they've been working. Their renewable energy market has been going for 15 to 20 years longer than the U.S. market has been going. So they've had time to figure this out. The other thing, the biggest thing about our transition to renewable energy for the entire country is our infrastructure, which is interesting. We can build as much wind and solar as we can. It can just blanket the entire United States, but we also have to pay for basically redoing the electrical grid, because a lot of it is not suitable or not suited for the amount of generation that would come from a solar farm or a wind farm. It's more suited to, it's literally designed exactly for the like one coal plant that it was built to address. So when we're starting to put all of these different solar farms and it's getting all of these different points of generation, we have to basically rebuild that part of the grid to accept that. And that's expensive. But we're also trying to, while we're doing that, transition into something called the smart grid, which will hopefully like be integrated with a lot of IoT and like very like stuff that, you know, our iPhone does, things that recognize a load and they adjust to the load. But there's a lot of research that still needs to be done on smart grid, and a lot of people are really scared. They're like, are these smart grid equipment items going to like spy on us or whatever? I don't know, but we have a lot of work to do on rebuilding the electrical grid in order to get there. So at the moment, at the speed we're going, I'm not sure if the Paris Climate Agreement is realistic, but ideally, I think it is. That's the route we should be going. Are you familiar with is it CCS, and think it's a viable decarbonization method? I'm not. There are a lot of different decarbonization methods though, and they're all still in the research phase. And if you want to be a research engineer and research decarbonization, that's like definitely something that's super needed. And I think there are like competitions in college for like engineers to work on decarbonization methods. And also just like, I read something the other day that there's a company out there who's like repurposing carbon dioxide into like the randomest things. Like they're trying to make carbon dioxide into jet fuel, which is really cool. So definitely something that is at the leading edge of that field. I don't know a lot about it, but I recommend looking into it as you grow as an engineer. Interesting study that showed America has more parking spaces than cars in comparison to Europe, who promotes biking. So it can definitely be systemic use of cars that would need to be addressed before being able to apply the creation of large scale renewable gas and maybe promoting biking. I think that would be awesome. I feel like that's why, like, because of America's dependency on cars is why the EV industry has been like so promoted, especially by our government. They just, you know, released a huge subsidy for creating electric vehicles. So hopefully that would help. Biking would be awesome. But as you guys know, as Chicago residents, biking in Chicago is kind of dangerous depending on how you bike. So I guess, yeah, biking would be cool. But I think that's what we're addressing hydrogen and electrical vehicles with. I think that should be our last question, if that's okay with everybody. Here's my contact info. If like, don't hesitate to reach out. I love like just helping people realize their renewable energy kind of path. And I love answering questions about like, how do I get there with like each step in college? Yeah, so email me, message me on LinkedIn, do whatever, spam me. Like, I love to help. So thank you guys.
Thank you so much for taking the time out of your day to help grow our knowledge of renewable energy.
We'll send this information in the event recap that we'll send out later today as well. So you can find that information there. And thanks again, Ms. Knobloch, for everything.
Absolutely. I hope to see you guys in renewable energy industry fields in the future.
All right. Have a good weekend, everyone.
Thank you.
Thank you so much.